All right, last time we started section 2.3 and we talked about the product and the quotient rule. In particular, I showed you that unfortunately, like all of the rest of our wonderful rules, it's sort of not intuitive. It doesn't do what we would expect it to do. You can't just take the derivative of the pieces and then multiply them, or the derivative of the pieces and then divide them. There are other ways to do those problems. So just as a reminder, let me show you each of those properties. This one was one of them, highlighted in pink. It says that if we're going to do the derivative of a product, we take each of the pieces and find their derivative, and we compile them back together by multiplying by the original of the other piece. So we had f of x times g prime plus f prime of x times g. So this was one of our two rules from last time. The second one was the quotient rule, and it's boxed in pink there as well. To do the derivative of the quotient, we actually need to take the original of the denominator times the derivative of the numerator minus the original of the numerator times the derivative of the denominator and divide by the denominator squared. And I showed you something that I had shown to me when I was younger than you, which was Hody Hi minus Heidi Ho over Ho Ho. Still what goes through my head, because one of those crazy mnemonic devices that some teacher told me kind of thing, right? Yeah. So this one was the quotient rule. And we did a couple of examples of each of these rules, and we got to the point where I wanted to show you also one more thing in this section, which is the derivatives of the other four trig functions. We did the derivative of sine and cosine in a previous lesson. What's the derivative of sine? Cosine. And what's the derivative of cosine? Negative sine. Very good. And we could use those along with the product rule and the quotient rule to derive the other trig rules. But I am going to just state what they are here. So on tangent, the derivative of tangent is actually secant squared of x. The derivative of cotangent is negative cosecant squared of x. And these two sort of feel similar. They both give us what like tangent turns into secant. The cotangent turns into the cosecant. Both of them end up squared, and the sign is positive on one, negative on the other. So there's these sort of a familiarity of these sort of being alike. The other two are also alike. The derivative of secant x is secant x tangent x. And the derivative of cosecant x is negative cosecant x cotangent x. So yeah, I don't think that we would consider those necessarily simple. They're not near as clean as sine becomes cosine and cosine becomes negative sine, right? They're not. But they do kind of occur in these sort of pairs that if you learn one of the two in the pair, you can kind of get the other one almost for free because of the similarities. So that part's friendly. All right, so we are going to use these rules along with product rule and quotient rule from this section to do a few more examples. So let's take a look at example number 5. Example number 5 gives us h of x, which is 1 over x minus 12 secant x. We've talked about in section 2.2 that we don't need a quotient rule when there's only one variable in one location. And that would be an example on this one. If you want to use the quotient rule, you can, but it's kind of like overkill. You know, like you're beating the chicken that's already dead kind of thing. Like it's just not necessary. All right? So the thing is that this can be simply written like this, and then I can use my simple derivative rules, my basic derivative rules. I can use my simple derivative rules or my basic derivative rules, and I don't have to get into anything complicated. So if I do a simple rewrite to start with, it makes life a lot easier on this problem. So what would the derivative of x to the negative 1 be? Right, it would be negative x to the negative 2, and we'll simplify or clean things up or whatever in a minute. What about the derivative of negative 12 secant x? Start with the negative 12. What's going to happen with my negative 12? It's going to stay there, exactly. And then what did we have for the derivative of secant? Yeah, secant x, tangent x. So the derivative of secant x is secant x, tangent of x. Okay, the only thing to clean up is the fact that the x to the negative 2 is written with a negative exponent, and it just didn't start out that way in the problem. So however the problem begins, we talked about this last time, is how we're going to put it in when we're done. And so we will rewrite this as negative 1 over x squared, and then minus 12 secant x tangent x. And that would be my cleaned up final version of the derivative. Any questions on that one? Okay, the next one is considerably more difficult. I have sines and cosines, so like that doesn't seem bad, but they are how? How are they combined? They're multiplied. This is a question I have used, or very similar to it, on tests before, and people mess it up all the time. Because these are multiplied, I can't just take the derivative of each piece and multiply them back together, right? That's what we wish could happen. It just doesn't work. So I have to remember that I'm working with a product, so I need a product rule. So let's take a look at what we would get if we do the product rule for this. So multiple versions of the product rule, what I do is I take the first term and I simply rewrite it. Sine x. And then we need the derivative of the second piece. So what is the derivative of cosine x? Negative sine of x. Product rule has addition between the terms. After that, we're going to write down the original of, well, I can't remember how I define it now. I usually do the derivative of the first piece next. Is that how I wrote it? No. I don't know. Derivative of the second one. Derivative of the first one would be derivative of sine is cosine x. And then original of the second one, right? There we go. Some version of that together. Yes, Jared?
In high school, we learned it like to remember it by was like 1d2 plus 2d1. Like the derivative in the 1d, like for the
Like this. Maybe you didn't write it quite like that, but that's what you just said, right? Yeah, so the first one times the derivative of the second plus the second one times the derivative of the first. Yeah, very good. Awesome. Okay, so it doesn't need a whole lot of cleanup, but we can combine these to be a little bit nicer looking. What happens when I multiply sine times sine? It's sine squared, so this is negative sine square root of x. And then cosine would also be the same, cosine squared of x. If you would like, you could rewrite it with the cosine squared first, so then it's minus sine squared. It doesn't matter to me in the slightest, but that would be what we would look at. Yep.
So would you ever simplify it down to like 1 since the second one of
So that's a good question. It wouldn't be minus 1. So what you're remembering is a trig property that says that sine squared plus cosine squared is equal to 1. And if I had that in my problem, I would want to do so. The problem is that because one of them is positive and the other one's negative, I don't have addition. So like even if I pulled out a negative, it would change this to negative in the middle, right? Actually, however, it is a trig identity. It's a double angle trig identity. It's not one we see used all that frequently, so I would not expect you to change it or anything like that. This is a perfectly reasonable way to leave the problem. So, but if I did have this, Maurice, you'd be right. We would be expected to realize that, oh, look, that should be the number 1, and we should simplify it to that. Yeah. Okay, so this one is done at this point. All right, let's take a look at a next one. Yeah. Okay, so this one has trig involved, and it also has what? A quotient rule. Yes, it does. So we've got trig and a quotient rule, and let's see what we can do to clean this up and simplify when we're done, because there probably will be a little bit going on this one. So with the quotient rule, we start with rewriting the denominator. So it's the denominator times the derivative of the numerator. So what is the derivative of 2 minus 3x? -3. Good. Quotient rule has subtraction in it, so subtraction is next. Now I need the numerator, which is 2 minus 3x, times the derivative of the denominator. So what is the derivative of the denominator here? Right, the derivative of tangent is secant squared x. So far, so good? Over what? Tangent squared of x. You're right. Good. Okay, so that right there is all the calculus that's involved. You did the calculus part. But it has been said before, and I will say it again today, that you will become much better at your algebra by taking calculus, because we simplify a lot of algebra and trig, but algebra really within calculus. So we're going to take a look at anything that we can clean up or simplify in what we have here. So let's see here. The first thing that we might recognize is that we have this sort of written in a funny way. It's tangent of x times -3, so I can rewrite that as -3 tangent x, right? That's better. I can also simplify and clean up the numerator, right? I can distribute this out and recognize that all my signs are also going to change at the same time. So I'm going to end up getting -2 secant squared of x and +3x secant squared of x. I think those are all the pieces. All over tangent squared of x. Okay, so for what we're going to do, we're leaving it there. Are there ways to change tangents into secants? There are. There's a trig identity, much like the one Maurice mentioned over here with the sine squared plus cosine squared equals 1. We're not going to go too far down a bunny hole here. That is not our goal. This is cleaned up as much as we really need it to be at the moment. If we were to want to start there and then take another derivative, we might have another discussion. And we will get there eventually, but for what we're working with right now, this is a reasonable place for us to give pause and call it good. All right, one more example with trig, quotients, and products. You see trig, obviously, because of sines and cosines. What else do you see? Quotient? Anything else? Yeah, I need to distribute. It kind of looks like there's a product. There really isn't, but you're exactly right. I need to distribute before I continue and into my problem. We'll make things a lot easier to clean that numerator up a little bit or simplify it by distributing a little bit before I start messing with the denominator versus the numerator. So if we can start right here instead. All right, so this is k prime of x. Please make sure that when you're writing down what you're finding, that you write down that you're finding the next thing. Please don't just write, I have some people who like to do this, just write equals. If I'm taking the derivative next, it's not equal to what I just had, all right? So make sure you're identifying, what it is you're actually finding here. You're finding k prime of x. All right, so somebody walk me through what I'm going to write down. I know I'm going to have a quotient when I'm done. Tell me what I'm going to write down first. All right, the denominator, which is 2 cosine x. Very good. Then what?
-3 cosine x.
Good. And Emma, that's from the derivative of the numerator, right? Good. And then you want to continue? Go ahead. Minus.
-2 sine of x
And that's the derivative of the denominator, yeah?
times 3 minus 3 sine x. All over 2 cosine, 4 cosine squared of x. Or
Okay.
2 cosine of x in square on top.
Yeah, we'll write it like that for a moment. You're right. Yeah. So all the denominator squared, which will eventually square the 2 in front of the cosine as well. Good. Okay, so it's a messier one at this point. However, it simplifies and cleans up pretty nicely as we continue working. So let's take a look what we have. If I clean up these two pieces right here and multiply these out, what am I going to have?
-6 cosine squared of x.
Good. And then over here, I need to distribute the negative and, whoops. Actually, you know what? Let's do it this way. How about I just distribute it right here? Are you good with that? And then I can distribute this piece next, so I don't have to worry about the signs upon signs upon sides going on. Okay, cool. So we're going to distribute the 2 sine x to 3, so that's going to give me what? 6 sine of x. And then I'm going to have, looks like, -6 sine squared of x. Does that look good? All over, and I'll go ahead and do what you suggested, Emma, to go ahead and rewrite it. This would be 4 cosine squared of x. Okay. Maurice, this is what you were asking me about on the last problem, or 2 problems ago. Does anybody see the simplification I can do on this one?
Negative cosine to negative sine, and then -1, and then we'll plot the 6.
Okay, these two are actually using this identity here at the bottom of the screen. Sine squared plus cosine squared equals 1. If I were to take a look at both of them and factor the -6 out of each of those terms, I would have sine squared on one of them, cosine squared on the other one. So the two pieces that are sort of marked in red right now combine to give me -6, and that's it, just plain old -6. And if it helps you to see it, I mean, you're welcome to, of course, rewrite them closer together and recognize that this is really what I have. You don't have to write this if you're seeing it just fine, no problem. But that's what I'm suggesting right there. And then I have the 6 sine of x still back over here. And all over 4 cosine squared of x. Okay, so this does in fact give me -6 plus 6 sine x over 4 cosine squared of x. Now what? One more thing I can do. Yeah, I can pull out a 2 from everything. Everything's even, right? I've got a -6 at the beginning, I've got 6 sine x, and I've got 4 cosine x, cosine squared of x. So each of those can reduce by a by a factor of 2. So this would be -3, this will be +3, and this will be +2. So the final result here, k prime of x, is going to be -3 plus 3 sine of x over 2 cosine squared of x. Any questions on that one?